For answers, we begin with R.N. Elliott, who pioneered this research in the 1930s and 1940s.
R.N. Elliott was a corporate accountant who specialized in financial restructuring. He was taken ill later in life, and during his recovery, took an interest in the stock market and began a detailed investigation.
Elliott identified an overall pattern to fundamental market movement. The pattern occurs over and over again in the markets. Soon he realized that if you can identify where you are in the pattern, then you can predict where prices are likely to go next. The basic pattern unfolds in 5 waves. The 3 waves in the direction of the main trend are labeled 1, 3, and 5, which are separated by 2 interruptions labeled 2 and 4. The essential form, then, is 5 waves of net movement in the direction of the one larger trend, followed by 3 waves of net movement against it, progressing in 3 steps forward, 2 steps back. Elliott further observed that these patterns were the same regardless of scale. The smaller versions linked to form larger ones, and so on. Bob Prechter became involved with Elliott's wave principle in the 1970s.
I'd been investigating methods of market analysis for quite some time. I got curious about this obscure idea called the wave principle. I wanted to know if some guy had imposed his idea of a pattern onto the market, or was it really there? I started keeping my own hourly charts, and I was quite amazed to find that he indeed explained the patterns that were there. I saw them over and over again, every hour, every day, every week, every month. So I had to know more. And first thing I did was I contacted the Library of Congress, and they didn't have his works, but I finally found them on microfilm in the New York Public Library. So I had copies made, and I found a wealth of material, a complete, all-encompassing theory of the stock market that had been lost to academia and Wall Street practitioners for all those years.
Prechter became so intrigued by the wave principle that he soon republished Elliott's original books in a volume called R.N. Elliott's Masterworks. In the meantime, he contacted financier A.J. Frost.
Frost had been a colleague of Hamilton Bolton's, who, along with a very well-known financial analyst named Charles Collins, kept Elliott's theories alive throughout the 1950s and 60s. And Frost and I just hit it off great from the first minute, and we decided to get together, consolidate all of Elliott's ideas, and put them into one volume.
The book Elliott Wave Principle would become the definitive guide to discerning the market's forms. Elliott Wave Principle has sold over 100,000 copies and has been translated into a dozen languages.
We've had now too high an inflation rate for the last 10 years.
In 1978, as inflation accelerated and after the Dow fell to 780, there was widespread pessimism. Elliott Wave Principle made a bold forecast for the financial future. This chart shows the Dow up to 1978. This chart shows Frost and Prechter's forecast. They expected a great bull market into the 1980s. The forecast came true. The bull market charged ahead further than Frost and Prechter expected, but the advance stayed true to form. It was one of the most highly emotional times in US history, and the stock market was shut down. The night of the tragedy, Prechter released a chart forecasting the S&P Composite Index.
Well, remember that in September 2001, the S&P had already been falling for a year and a half. So by 9/11, it was just days away from finishing 5 waves down, which means it was days away from the start of a very big rally. And that's exactly what happened. Terrorism threw almost everyone off, but it had absolutely nothing to do with our outlook. I mean, there was no terrorism at the high in 2000. It was almost all good news, and that's when you were supposed to be selling. So, sure, waves can throw you off now and then, but if you try to follow the news, it will almost always make you do the wrong thing. The wave principle can also be used to forecast macroeconomic changes. To investigate this, I went back to the charts and I compared changes in social mood against the occurrence of economic expansions and recessions. And what I found was that changes in the economy do not precede and cause changes in social mood, which is what most people think. But in fact, it was the opposite. The social mood changes preceded changes in the economy.
As it turns out, the mathematics behind nature's most vibrant forms play an important role in the wave principle and socionomics. What Elliott described decades ago today are called fractals, which are irregularly shaped objects that are self-similar at different scales. This self-similarity reveals order in many natural objects that at first glance seem random.
What R.N. Elliott discovered 40 years ahead of modern mathematicians is that the stock market is a fractal. Not only that, he said it's a specific fractal. That's one heck of an achievement for somebody without a computer.
The invention of the silicon chip in the 1970s created a revolution in computers and communication, and hence transformed our way of life. We are now seeing another revolution, which is going to change our view of the universe and give us a better understanding of its working.
I'm Arthur C. Clarke. I write science fact and science fiction. You may know my movie 2001: A Space Odyssey. I've seen some remarkable developments and inventions in my lifetime, but one of the most extraordinary is the Mandelbrot set and fractal geometry. This film will explore the fractal universe, and on our voyage of discovery, we'll be helped by Professor Ian Stewart of the Mathematics Institute, University of Warwick, and author of over 100 published scientific works. Dr. Michael Barnsley, former professor of mathematics at Georgia Institute of Technology. Finally, Dr. Benoit Mandelbrot, whose unorthodox mathematics led to the discovery of the Mandelbrot set and fractal geometry.
Mandelbrot's fascination with the visual side of math began when he was a student.
It is only in January '44 that suddenly I fell in love with mathematics, and not mathematics in general, with geometry in its most concrete, central form. That part of geometry in which mathematics and the eye meet. The professor was talking about algebra, but I began to see in my mind geometric pictures which fitted this algebra. And once you see these pictures, the answers become obvious. So I discovered something which I had no clue before, that I knew how to transform in my mind instantly the formulas into pictures.
It was 1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live: the computer. IBM was looking for creative thinkers, nonconformists, even rebels. People like Benoit Mandelbrot.
In fact, they had cornered the market for a certain type of oddball. We never had the slightest feeling of being the establishment.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description there were these other things. Things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end. And now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said, well, you start with an equilateral triangle, one of the classical Euclidean geometric figures, and on each side
I take a piece and I substitute 2 pieces that are now longer than the original piece. And for each of those pieces, I substitute 2 pieces that are each longer than the original piece.
Over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve, because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long your yardstick is, how much patience you have. If you measure the coastline of Britain with a 1 mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1 foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number.
Because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called "How Long is the Coastline of Britain?"
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
What we would think of as normal geometry, one dimension is the straight line, 2 dimensions is, say, the box that has surface area.
And 3 dimensions is a cube. But could something have a dimension somewhere in between, say 2 and 3? Mandelbrot said yes. Fractals do. And the rougher they are, the higher their fractal dimension.
There are all of these technical terms like fractal dimension and self-similarity, but those are the nuts and bolts of the mathematics itself. What that fractal geometry does is give us a way of looking at, in a way that's extremely precise, the world in which we live, in particular the living world.
Mandelbrot's fresh ways of thinking were made possible by his enthusiastic embrace of new technology. Computers made it easy for Mandelbrot to do iteration, the endlessly repeating cycles of calculation that were demanded by the mathematical monsters.
The computer is totally essential. Otherwise, we've taken a very big, long effort.
Mandelbrot decided to zero in on yet another of the monsters, a problem introduced during World War I by a young French mathematician named Gaston Julia.
Gaston Julia, he was actually looking at what happens when you take a simple equation and you iterate it through a feedback loop. That means you take a number, you plug it into the formula, you get a number out. You take that number back to the beginning and you feed it into the same formula, get another number out, and you keep iterating that over and over again. And the question is, what happens when you iterate it lots of times?
The series of numbers you get is called a set, the Julia set. But working by hand, you could never really know what the complete set looked like.
There were attempts to draw it, doing a bunch of arithmetic by hand and putting a point on graph paper.
You would have to feed it back hundreds, thousands, millions of times. The development of that new kind of mathematics had to wait until fast computers were invented.
At IBM, Mandelbrot did something Julia could never do: use a computer to run the equations millions of times. He then turned the numbers from his Julia sets into points on a graph.
My first step was to just draw mindlessly a large number of Julia sets. Not one picture, hundreds of pictures.
Those images led Mandelbrot to a breakthrough. In 1980, he created an equation of his own, one that combined all of the Julia sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julia sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
It's not easy to describe the Mandelbrot set visually. It looks like a man, it looks like a cat, it looks like a cactus, it looks like a cockroach. It's got little bits and pieces that remind us of almost anything that you can see out in the real world, particularly living things. So it has a character that reminds us of a lot of things, and yet it itself is unique and new.
The Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and find the same, describe the same thing. It's a common experience. And so such things that can be magnified forever and have infinite precision do exist, but they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
With this mysterious image, Mandelbrot was issuing a bold challenge to long-standing ideas about the limits of mathematics.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
The Mandelbrot set was a great example of what you could do in fractal geometry, just as the archetypical example of classical geometry is the circle.
When you zoom in, you see them coming up again, so you see self-similarity. You see, by zooming in, you zoom, you're zooming in, and pop. Suddenly, it seems like you're exactly where you were before, but you're not. It's just that way down there, it has the same kind of structure as way up here, and the sameness can be grokked.
Now we'll begin our serious exploration of the Mandelbrot set. A voyage which, in fact, could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier, the M set, is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big. But this is really infinity. What is so remarkable, in fact, astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history, and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers.
I think the
application is that from very simple formulas, you can get very complicated results. It's fundamental from viewpoint of the very base of science, because what is science? We have all this mess around us, things are totally incomprehensible, and then eventually, more or less rapidly, more or less hard to achieve, we find simple laws, simple formulas. In a way, a very simple formula, Newton's law, which is just also a few symbols, can, by hard work, explain the motion of planets around the sun and many, many other things. The 15th decimal, it's marvelous. A very simple formula explains all these very complicated things.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals z squared plus c.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane defining the location of a spot.
Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of a two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves.
This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on.
When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line.
So what we get from this basic iteration is a kind of map, dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction.
Think of a computer screen. You're looking at each individual little element, each pixel of the screen. You pick one of these pixels, you apply this rule lots and lots of times, and either the pixel moves off and disappears completely from view, or it moves in towards a fixed point in the middle of the screen. And what you do is, you just want to distinguish between going off out to infinity or going into zero. So any point that moves into zero when you apply this rule, you colour that point black. And any point that goes off to infinity, what people tend to do is colour it all sorts of wonderful rainbow hues about how fast it goes away. The important bit's the black bit in the middle. That's all the stuff that doesn't escape when you keep applying this rule.
I'm sure it's occurred to you that the Mandelbrot set looks like some kind of strange insect. It certainly has an organic feeling about it. It's got warts all over it, and it's also quite hairy. If we go out along one of those hairs, we find something rather interesting. Now look what's happening. At the tip of each hair, it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realized he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
It took a long time for us to emerge and start to look out at the other part of the physical observable universe, not as narrow studied little entities, the scientist who studies the flea on the back of the flea on the back of the flea, but rather being able suddenly to look out at the totality of nature and then say, my goodness me, we've got nothing to describe this with. Clouds are not made with straight edges. Trees are not circles. They're not triangles. They're something very, very different indeed. But there's a continual kind of a pattern that I can see as I look at the edge of a rising cumulus cloud, one of those very, very wrinkly, coruscated clouds that has such fine structure in it. And you say, but there's no lines or circles there. The wonderful discovery has been that there's an extension of classical geometry, Euclidean geometry, which is called fractal geometry.
Fractals are shapes which we are extraordinarily used to in, how to say, our subconscious, ill-organized life. For example, everybody knows that if you take a map of Britain on a small school globe, you see a very simplified shape. Cornwall is just a kind of triangle, and Wales perhaps a little rectangle. You cannot put the details on a small map. If you look at in a larger map, you add more detail. The closer you come, in a certain sense, imagine yourself like somebody coming on a rocket. From far away you see very little, and the closer you come, the more detail you see. If we come very, very close, you begin to see rocks, and finally the idea of coastline disappears, because one doesn't know any longer where is land and where is water. So indeed arose in my mind to put together a geometry based upon many known facts in mathematics, scattered facts in mathematics, many scattered facts in our experience, many scattered facts in the results of what scientists had done of various kinds, all kinds of putting together all these things and using them as bricks, if you will, of a new building, which is a new geometry, which is a geometry of shapes which are equally rough at all scales.
One of the revolutions in thought that's resulted from this discovery is the realization that nature deals not in smooth, continuous objects, as we always imagined, but more often in fractals. And I'd like to show you how she does this. Now I'm going to generate a fractal before your very eyes. What you see here is what's called the seed, and it's an appropriate word in this case. Those two lines represent the first generation of the formation of a geometrical figure. And the computer has been told to continue growing these lines, but changing the direction every so often and at different distances. Now that's a very simple set of instructions, but look what happens after they've been carried out for, say, 10 generations. The tree I showed here, and it does look very much like a tree in nature, is symmetrical because the two branches at the beginning were the same length, off in the same direction. But if we change the length of one branch and change the direction, look what happens. In a way, this is a more realistic tree than the first one, because in nature you seldom have perfect symmetry. Much more elaborate structures can be created by very similar rules. I'd like to emphasize that all these shapes or objects, or whatever you call them, although they look real, are generated entirely in the computer by following out a few simple instructions and repeating them over and over again. This is the way in which nature creates things.
It's exactly like the DNA in a butterfly's egg. Somehow that unravels and unrolls to form the extraordinary and beautiful pattern on a butterfly's wing with its myriads of colors and form. Somehow it's hidden in that seed, in the DNA, and not only that, but the wings themselves probably only occupy a relatively small part of the total DNA. They are, if you like, a little formula that is unraveled by the process of growth and deterministic following of rules to form this natural and beautiful thing.
A fractal is not the only ubiquitous natural phenomenon whose essence is its form. Another is the spiral. The logarithmic spiral depicts growth and expansion in the universe. For example, if we look at the branching tendencies of a tree, we see that as time progresses, one spiral expands as the number of branches increases, and another spiral contracts as the circumference of branches decreases. Spirals are reflected in structures as diverse as seashells, pine cones, sunflowers, whirlpools, and hurricanes. And as with fractals, we can see spirals at many different scales, from the growth of an embryo to a galaxy. So how do these spirals connect to socionomics?
The idealized depiction of the stock market's progress can be seen as a spiral. The top of each successive wave of one higher degree serves as a touch point for the exponential expansion. And pretty soon it begins to look like the pattern of a hurricane or galaxy. Now, what are stock prices? They are humanity's valuation of its own productive capacity. So human progress and regress form one of nature's growth patterns.
Fractals and spirals reveal an underlying order within many structures that on the surface seem chaotic. Progress and growth seem to occur naturally by these forms. But there could be an even more intimate connection to nature. In the 13th century, a mathematician named Leonardo Fibonacci discovered an important number sequence.
It's a very simple sequence of numbers, starting with the number 1 twice. Each succeeding number in the sequence is the sum of the 2 preceding ones. So the sequence goes 1, 1, and 2, and 3, and 5, and so on. And for reasons that are pretty mysterious, this sequence of numbers seems to appear in a wide variety of places in the natural world.
R.N. Elliott observed that the fractal he called the wave principle was built according to the Fibonacci sequence of numbers, which is governed by a ratio called the golden mean, or phi. The ratio of any two conjugative numbers in this sequence approaches phi. That is an irrational number, which is approximately 0.618. If you look at the Elliott wave patterns, these patterns involve a certain number of waves called impulse waves and corrective waves. Each type of wave, when broken down into its components, reproduces the Fibonacci sequence as the degrees of subdivision increase.
The 5 waves of progress and 3 waves of regress is the essential form of markets. If there were no fluctuation, there would be no change. So you need at least 3 waves to get fluctuation. Therefore, the 5-3 pattern is the most efficient way of achieving both fluctuation and progress. Nature is efficient, and this pattern is no exception.
The importance of the Fibonacci sequence in nature, just like the importance of fractals and spirals, is its ability to create a robust and efficient method of growth. There's a wealth of biological, psychological, and sociological evidence that supports the connection.
For example, the Fibonacci sequence is in flowerhead arrangements. In this example, notice how from stem to tip it subdivides 1, 2, 3, and 5. In the human body, we find a Fibonacci branching pattern as well. 5 appendages, encompassing legs, arms, and head. 3 subdivisions within the arms and legs. 5 subdivisions off the hands and feet, and 3 subdivisions in the fingers and toes.
Then we find the Fibonacci ratio in heart muscles, in bronchial tube branching, even in the electrical potential of neurons, and as Roger Penrose pointed out, even in the arrangement of the brain's microtubules.
The DNA molecule, the code for life, is made up of 2 intertwining spirals. We find the 0.618 ratio between the helix's width and cycle length.
The Fibonacci ratio may even regulate the way we think.
In the 1950s, psychologist George Kelly tested the judgments people make on a positive-negative scale. He assumed that in value-neutral situations, the average response would be 50-50, but he found that in fact, it's 62-38, consistently weighted towards the positive or optimistic side. Researchers have confirmed his findings in numerous studies.
For example, when you ask people to judge how dark a piece of gray paper is, the answers don't produce a bell curve as you might think. They bulge at the 62% point. If you ask subjects to sort objects into two piles, or rate acquaintances' character traits, or make choices in situations of uncertainty, you get the same result.
This bias extends to collective behavior. Stock market analyst Robert Ray showed in the early 1930s that, on average, bear markets tended to relate to bull markets by the Fibonacci ratio in both time and price. And recent studies show the same tendency in voting patterns.
It's easy enough to imagine that, or make claims, well, this Fibonacci sequence and the way that it appears in very many areas of life is just like some kind of number mysticism. It's equally easy to take the position to say, look, when the same thing keeps occurring in such a wide spectrum of areas, there has to be some underlying reason for it. I tend to the latter point of view.
The robustness, resilience, and efficiency of all these universal forms, spirals, fractals, and Fibonacci relationships, may be connected to collective social mood. Nature prefers the most efficient path. In the case of the wave principle, though, the efficiency is not in the individual's biology, but the efficiency in the progress of the species.
The idea that fractal patterns, spirals, and Fibonacci growth all exist in the stock market is certainly remarkable. But then when you consider that the stock market itself is a measure of humanity's productive capacity, and then when you consider that cultural trends ebb and flow with that pattern, I mean, the resulting implications are quite grand, really.
Frost and Prechter stated in Elliott Wave Principle that the same law that shapes living creatures and galaxies is inherent in the mentation and activities of human societies.
Living creatures seem to be complicated structures produced from simple rules, simple laws of physics and chemistry. And a lot of the structure that you see in living creatures is organic but pattern structure. Leaves on trees, ferns particularly, things like that, have the same feature that the Mandelbrot set has of you look at little pieces of them and they have lots and lots of detail. And in fact the little pieces look very similar sometimes to the whole thing. It's very tempting to compare the way a simple formula produces a complicated Mandelbrot set with the way very tiny things in nature produce complicated organisms. And there are certainly some similarities in that there is the same kind of unfolding of a process. The instructions are there, but not an actual description of the object.
Once you develop a fractal geometer's eye, you can't help but see them everywhere. Every single thing you see is one way or another described by reference either to itself or to something else in the picture you see. It's as though you're staring at a vast dictionary, but the dictionary words are bits of pictures, and the references, the definitions of the words are made with other bits of pictures. And so you stare at one picture. I look out in the garden and at the trees, and I see this set of relationships between the picture and other bits of the picture. Those relationships are no more nor less than the assertion, from my point of view, that what I'm seeing is fractals everywhere.
A classic example of a fractal is a stalk of broccoli. The whole stalk is a similar version of the individual piece that grows on the top. If you break that off, you're left again with a similar version of the whole stalk. This relationship has proved to be universal in nature, as represented by mountain ranges, cloud formations, and the distributions of galaxies.
A common characteristic of fractal systems is branching. Trees, circulatory systems, and rivers, for example, all display branching fractal patterns.
There are lots of fractal systems within the body. In my work on the heart is actually full of fractals. The most famous example of it is the blood vessels coming into the heart. The coronary circulation is a pattern of a branching network of blood vessels that's typically fractal, where the branching structures look very similar at different scales.
Even snowflakes, known for their dissimilarity from each other, display a fractal pattern internally.
Of the many definitions that we may choose for a hologram, perhaps one of the simplest and the most eloquent may be as follows: that a hologram is simply a pattern that is whole and complete unto itself, and at the same time it's part of an even greater pattern that is whole and complete unto itself, while at the same time is part of an even greater pattern. Now, this pattern can be non-physical energy, or it can be very physical matter. The cells of your body are holographic in nature. One cell has all the information it needs to create another one of you. It is whole and complete unto itself, and it's part of an even greater pattern that you call your body.
One of the things that you point out in the holographic universe is that this is a model that's been around now for a few decades, but it's really beginning to show its power in explaining many, many areas of personal experience and science. At the same time, can we talk a little bit about how the model developed?
Sure. It was developed by two men, University of London physicist named David Bohm, who was a former protege of Einstein, and a Stanford University neurophysiologist named Karl Pribram. And they worked independently. Pribram was studying memory and found that there's evidence that the brain operates holographically. And Bohm was studying subatomic physics and found that on the subatomic level, the fabric of reality seems to possess properties that are reminiscent of a hologram. So if you put those two ideas together, that our brain seems to be holographic and the universe is holographic, it suggests that maybe it's compelling evidence that the universe may be a kind of hologram, not that it's literally a hologram, but that it's a good metaphor or way of understanding the universe.
Now, when you say it's holographic, what do we mean, really?
That, in a nutshell, that reality may be more plastic and changeable, like an image, than a solid construct, a sort of sticks and stones world. It has a couple of other implications, one of which is that a hologram has an unusual property. If you take a piece of photographic film that has a holographic image encoded in it, that means that you cannot see the image with your naked eye. You have to reconstruct the image, you have to shine a laser through it. So if you have an image of a rose in the film, shine a laser through the rose, you'll get a three-dimensional image of the rose on the other side. You cut that film in half, shine a laser through each piece, you'll get a whole rose out of each piece, which is a very unusual property and sort of boggles the imagination at first. Cut it in 4, you get 4 roses. Cut it in 8, you get 8 roses. So the universe is a hologram. It means, as William Blake said, that quite literally you can find the universe in a grain of sand, that every portion of the universe contains some semblance of the whole universe.
That's very profound.
Very.
It's mind-boggling, and you know, one of the things that you point out in a footnote of your book that I would like to mention is that this doesn't apply for many of the kinds of holographic images that are popularly sold as pendants and the like that don't require laser light.
Right. Every talk I give, someone comes up and says they cut the hologram in half on their credit card and ruined it and didn't get the effect. And it only applies to those images that you cannot see with the naked eye, that you have to reconstruct.
If you were to look at holographic film, it might look like ripples on a pond unless the laser light is shined through it.
Right. There's no decipherable image in the film, and it very much does look like ripples in a pond, like when you drop pebbles into a pond. There are all sorts of little circles.
They're called interference patterns.
Right. The same as when you drop 2 pebbles in a pond and the ripples crisscross. That is exactly what is in the film. It's the crisscrossing of the laser light that's recorded on the photographic film.
So there's the sense about a hologram that there's 2 levels. One is this 3-dimensional image that's projected, and it can look so real that you want to reach out and touch it. And then the other level are these interference patterns.
Right. That reality in a hologram can manifest in 2 ways: as a concrete image, or as this sort of indecipherable blur of energy. And an analogy to this is kind of when you're watching Johnny Carson on your television set. That's really, his image is encoded in 2 ways. One is as the concrete image on the TV set. One is as the blur of radio waves permeating the living room. And if the universe is a hologram of some sense, in some way, it suggests that there may be two very drastically different levels to reality, that the concrete reality we see, you know, when we look at these chairs and at the, you know, the trees and the clouds and everything like that,
our bodies
are just one way that reality manifests, and that at some deep level there's a level of reality where everything dissolves into an ocean of energy that is holographically interconnected, where every portion of the universe is contained in every tiny area of the universe.
Let's go back to the Mandelbrot set and look at some more of the strange flora and fauna of the Mandelbrot Zoo. There's a certain similarity between these shapes. You can recognize they're cousins of each other, and yet they're all different despite their similarity. There's an infinite variety here, just indeed as there is in the world of nature. We see shapes that remind us of elephants' trunks, tentacles of octopi, seahorses, compound insect eyes. There's some connection between the Mandelbrot set and the way nature operates. I'm looking at Saturn, one of the most beautiful objects in the sky. In fact, we've discovered quite recently that the beautiful rings of Saturn, which have intrigued astronomers for centuries, do illustrate some of the phenomena we've been discussing in the Mandelbrot set. As you go closer and closer to Saturn, you see more and more detail which no one had ever dreamed of before the space age opened and we were able to get close-ups of Saturn and its rings. It's not surprising that when we have so many examples of fractals and related phenomena here on this planet, there are even more in the heavens.
To me, just looking up at the Milky Way is staring at a fractal. It's got an extraordinary dotty character, and yet if you take a magnifying glass to it, that is a telescope, and you look at it ever closer, you find that there are hundreds and thousands more little dots where you thought there was almost none. So you get an immediate example of a structure that seems to go in and in and in with more and more detail.
It can now be seen that there is, in fact, some kind of transcendental object. And it's best to try and describe it phenomenologically. We don't know what it is, but we do know that it's an enormous attractor of some sort, and we are in the field of attraction, and by we I mean all life on the planet is being drawn into this nodal point, and it is possible to anticipate it through the psychedelic experience, because apparently the natural and the linguistic world are worlds which are organized along the principle of fractal curves. Fractal curves are recently discovered mathematical objects. Not all of them are recently discovered. Some were known as late as the late 19th century, but most have been discovered using computers in the last 10 or 15 years. And they are self-similar curves such that when you take a subset of one of these mathematical objects, it is found to have the whole pattern embedded in it. The Fourier transforms that describe holograms are these kind of things. Coastlines, mountain ranges, data of all sorts, when analyzed in a certain way, is found to be fractal. Apparently, the world is a kind of vast spiral fractal that is achieving greater and greater closure with itself. And we experience this density of closure and this compressionism as the spectrum of effects which we call human evolution, human history, emergence of high technology, the present moment, the rush toward apocalypse. The most intense moments that the universe has ever known are the next 15 seconds. And beyond that lies still more intense moments. Novelty, as a kind of generalized paradigm of the compression of connectedness throughout the cosmos, is accelerating moment by moment in the rocks, in the trees, in the stars, and in us. And so what we call history, which is not as modern, the modern theory of history is that it's what they call trendlessly fluctuating. That's their model of the world. You get order at the atomic level, order at the biological level, order, 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 and suddenly you reach human beings, trendlessly fluctuating. It's as though, you know, we were Brownian, affected by the Brownian movement of random particles, and yet we somehow, out of all this ordering, we're to believe that then emerges the trendless fluctuation of human history. Actually, this is nonsense. It's simply that there has never been a thoroughgoing theory of history. However, now we are ready for them, because these wave mechanical ideas, the notions of closure, Sheldrake's idea about the presence of the past, the way in which the past drives the present, all of these things lay us open for an understanding of the compression and densification of time. And this is what is experienced in the psychedelic experience. Really, you know, Whitehead said of Dove Gray that it haunts time like a ghost. Well, I think that the compression of the three-dimensional universe at the end of time haunts time like a ghost. It's the cosmic giggle. Here a messiah, there a shaman, there an ecstatic poet, and there the tiny ripple that is simply a congruent coincidence in the life of a single individual. Robert Anton Wilson called this the cosmic giggle. It's when something protrudes through the forward-flowing momentum of rational casuistry and causes it to flow around it and eddy and churn, and then you see through for a moment, and you say, well, what is it? There was a plottedness for a moment. There was the hand of the maker there, but now I don't see it anymore. That is the going behind the veil. That is the seeing into the structure of being that lies behind the conventionalized languages.
Here is the most important fractal of all in the human body. A small portion of the incredibly complex wiring circuit of the brain. We may never understand how our brains work, but if we do, I suspect they'll depend on some application of fractal geometry. Why I think there may be some connection between the Mandelbrot set and the wiring of the brain is because when I close my eyes and press my fingers against my eyelids, I see these patterns. I'm sure you're all familiar with them. You also see them when anybody gives you a bang on the head. Well, sometimes these patterns echo some of the shapes of the Mandelbrot set. Also, I am told, I have never tried the experiment myself, that when certain illegal chemicals are ingested, you experience visual hallucinations strikingly similar to some of the patterns of the Mandelbrot set. Why do these strange patterns have such an appeal? Well, obviously they trigger some kind of resonance in the mind. And incidentally, as an odd coincidence here, the name Mandelbrot and the word mandala for a religious symbol. I'm sure it's a pure coincidence, but indeed the Mandelbrot set does seem to contain an enormous number of mandalas or symbols. The Paisley pattern is one, and I'm sure there are many others.
So that implies that this notion that we go about our everyday lives with thinking of ourselves as separate from each other, and the cup is separate from the coffee that goes in the cup, that these notions are somehow, what would you say, superficial or contradicted at a deeper level?
They're artificial, definitely, and Bohm really stresses this, and it's a very interesting notion, because in our Western way of thinking, we're so attached to the idea that when we come up with a concept like an apple or an electron or whatever, that exists out there, and we forget, it's kind of like fish unaware of the water in which they swim, that the conceptual pigeonholes we use, words, to describe reality, are phenomena inside our head. They're not out there. And most of the time this is a philosophical quibble, but when you get down to quantum physics, and this is one of the reasons that Bohm came up with the holographic idea, it starts to have real effects. And one of those is it's been discovered that if you take two subatomic particles like electrons, in certain instances, when you do something to one, it will always affect the other, no matter how far apart they are. It's kind of like stories that you've heard of identical twins, where when one is hurt, the other feels the pain. And the problem is that we can find no process known to physics that explains how these could be sending a signal back and forth. In fact,
because it would have to be faster than the speed of light.
Instantaneous. It would have to be an instantaneous signal, and Einstein's theory of relativity said you can't have instantaneous signals because it would mean that you could violate the time barrier and conceivably call your grandfather and tell him not to marry your grandmother. And most physicists say, well, this would be just too troubling to incorporate into a rational picture of reality. Bohm explains it in a different way, which is a very interesting way, and he says, if you imagine that you've got an aquarium in which you have a fish swimming, you have a TV camera facing the front of the aquarium, one facing the side of the aquarium, and you have a monitor attached to each camera. Now you also imagine further that you come from a culture that's never seen aquariums, never seen fish, never seen monitors or cameras. All you are privy to is the two images on these screens. He says that maybe, you know, if you look at these two screens, you're going to see a side view of a fish and a frontal view of a fish. And because you don't know what the deeper reality is, the reality of the aquarium, you may assume that these are two separate things. But
two different fish.
Two different fish, two different objects. But every time one fish moves, the other is going to make a corresponding movement. And you may then jump to the conclusion that somehow the one fish is signaling the other, or communicating the other to say, hey, do this, instantaneously. And Bohm says this is what we've done with subatomic particles, that we assume that an instantaneous communication is going on, when that's not really what's going on at all. At a deeper level, a very holographic level of reality, every particle in the universe collapses to a sort of cosmic unity. They're not signaling each other. They're like that fish where there's the level of the aquarium. And so what that means, talking about words, is that there is no separation between electrons. Furthermore, there's no separation between people. And this has all kinds of very boggling implications, one of which is that we've always tried to understand, for example, psychic phenomena, like how could I get information out of your head in my head, as some sort of signal going back and forth. But if we're organized, if we live in a universe that's organized holographically, you no longer have to tackle it that way. It could be that I have the entire universe and every neuron, every cell, every atom, every electron in my head, and you do also. So when we can access that, we can access information that seems to be beyond our normal sensory reach. Pribram was working under a very famous neurophysiologist named Carl Lashley, and it was at a time when it was believed that memory was stored in a specific spot in the brain, and there was something called the proverbial grandmother cell, that there was literally a cell in your brain that contained the memory of your grandmother, what you knew about your grandmother. And so they did a rather gruesome series of experiments for animal lovers, but it came out with some very profound information. They took rats and they taught them how to run mazes, and then they would surgically remove various portions of the brain, Pribram and his mentor Carl Lashley. The reasoning being that if they could remove a portion of the brain and the rat could no longer run the maze, they'd found the area of the brain where the rat's memory of the maze running ability was encoded. Now every time they removed a different portion of the brain, they discovered that they could never remove the memory of how to run the maze. They could impair the rat's ability so it might limp through the maze, but they couldn't remove it. And really, surgeons had known this for a while, doctors had known this for a while, because when people have head injuries, they don't forget half of the alphabet or half of their family or half of a novel they read. They have global memory impairment where their entire memory may be hazy. But memories don't seem to be stored in our heads in the same way that books are stored on a shelf. And it wasn't until the 60s when Pribram encountered the holographic model that says that the whole is contained in every part that he said, aha, this may be what's going on in the brain.
how can a point contain the whole if a point has a finite boundary? You know, if the body has a finite boundary, how can it have infinity in it? So I was like, oh, I gotta go back to the drawing board on this one. And I was like, that doesn't really work. How do I do this? Well, it turns out that that's gotta be one of the largest errors that is going on in our understanding of physics and our understanding of the way the universe functions and our place in it. That is, that infinity and finite system are opposites instead of complementary. But how can a finite system and an infinite curvature be complementary? How can the two be together? I knew when I was 10 that there was a solution to this, because I knew I was right, because I had seen it in my mind's eye. I instinctively knew it. Actually, most children I talk to, if they haven't gone through that first lesson of geometry, know this. They think of the universe as infinitely big and infinitely small, all embedded into each other to infinity. In general, they think of that as being quite logical. The kids are not the only people that thought of this. Well, that the concept of a universe coming out of a dot is not that outrageous. The current theory of the Big Bang says that we all came out of a dot the size of a Planck's length, 10 to the minus 33 billions of times smaller than an atom, and all of our universe. The only difference here is that this view says, no, it didn't all emerge from one dot that decided to make a universe. All dots contain the possibility of a universe in it. All dots are connected to all other dots. Again, how do you fit infinity in a finite space? And it's crucial that we understand how we did it. Well, when I grew up, eventually, I found the solution. I found the answer to this. The solution is what is called a fractal. Now, if I give that equation to my computer and got the computer to just keep making boundaries, keep making smaller and smaller triangles, it would continue to do this to infinity until it heated up, melt down, and I'd have to go and get myself a new computer. But assuming it didn't do that, it would keep making smaller and smaller triangles to infinity. And I could give it a code so that every 5 iteration or 6 iteration, it would zoom in so you could see it again, and then starts making more triangles, and then zoom in, and then so on to infinity. However, although I can place an infinite amount of triangles, I will never exceed the first boundary I made for myself. Never. I just showed you how infinity fits in a finite space, or a so-called finite space. Because you can divide to infinity within the circumference of a circle. What does that mean? Why is that important? We built faster and faster and faster accelerators that cost billions of dollars to build, to get smaller and smaller and smaller and smaller particles. Now we're at like millions of times smaller than an atom particle, actually. And we're building accelerators now in Geneva, in Switzerland, that are costing $300 billion, I believe. 5 countries had to get together to build it, right? To get even smaller particles. Well, if we understand this principle, we would understand very quickly that you can keep building larger accelerators and you can keep getting smaller and smaller particles. You can always keep dividing. So we would give up the search for some fundamental particle and that's going to end the search for particles, and we would start to understand that what we need to discover is the dynamics of the division, not, you know, how far we can go into infinity. Just so that some physicist can put his name on it and get a Nobel Prize for a new particle. Every one of your atoms, every one of your cells has infinite potential in it, has infinite connectivity to everything else. That each one of your atoms is a mini black hole. Because if there is infinite amount of particles in it that can be divided, that means it has infinite mass. It seemed to say as well that the universe would be expanding and contracting, right? If everything goes towards infinity at the center of all atoms, then the universe is contracting as much as it expands. And I could see how the external part of my existence is the expansive part, and the internal part of my existence is the contractive part. So I started to think in those terms when I was actually 11, and I learned to meditate. A young master of meditation from India taught me to meditate. And I was really excited because I was discovering a whole world within myself that seemed to have infinite potential. So I started to spend more and more time concentrating inward and connecting with that part of my existence. And I started to think that there must be a balance between the expansion of the universe and the contraction of the universe. And the contractive part of that balance equation is the part that generates. And the radiating part is the part that alienates, that destroys. Yet, all of our science, all of our knowledge is based on the radiating part. There's nothing we've really discovered since fire. We explode everything. We put fuel in a rocket, right? Tons and tons of fuel, and we light the bottom, put a few people on top, and pray that they're going to survive the experience. That's our approach. We put fuel in our car, and we explode it in a chamber, and we push a piston up and down. It's all about explosion. And we think the universe is expanding. When much later, I was brought to Georgia Tech to have a conference, kind of a debate with other physicists. These are very well-known physicists, highly regarded, older people that had their students there. And we were talking about things. Some of the students were there. They came in and out. We were, looking at equations. We had all this stuff on the big wall there, on the blackboard. And I showed up with this book. This is the only book I had with me. I had maybe another few, Well, that was my main book. It's called Gravitation. It's a classical book about relativistic equations. It's written by Messner, Thorne, and Wheeler. Those are legends of physics. Wheeler having worked with Einstein and so on. And it's a brick, you can see. And that's why it's called gravitation. When you pick it up, you know everything you need to know about gravity. And I was going through all the equations, and I could see that the physicists were starting to get upset with me. I was, kind of going through, the way they think of the universal dynamics and the universal expansion and all this. And I finally said, okay, if I understand your model right, and I opened Gravitation on page 719, and I said, if this is correct, then the universe is something like this, which they show you after about 1,000 equations. The model for our universe is a balloon with pennies glued to it. So what you do is you take a balloon, you take a bunch of pennies, and a glue gun. And you glue the pennies to the balloon, and the pennies represent galaxies. And then as the balloon inflates, the galaxies move away from each other, generating the universal expansion we observe with the Hubble. It's called the Hubble constant, or the Hubble expansion, and is observed by various modalities, including telescopes. And so I'm going through this with them, and you got to realize these guys are very accomplished physicists, and they're looking at me going, oh my God, this is like kindergarten stuff. If you don't know this stuff, you should go back home and study a little more before you waste our time. And so I was like, well, what I want to know is where is the equation, because I really looked through all your stuff, and where is the equation for this guy? The room became quiet. And I was saying, well, this is definitely a component of the dynamics that are going on, and I said, if you keep drawing, if you don't stop at the face, and you keep drawing the rest of the guy, you'll notice that when the balloon expands, the lungs contract. For every action, there's an equal and opposite reaction. First law of physics. That hurt. Everybody had a blank look on their face, and the room became so quiet you could hear a pin drop. And I could see my dear friend and sponsor across the room going, oh, you're doing damage. Kind of obvious. Completely missed. Obviously, if the universe expands, then something is contracting. And that dynamic of expansion would be a feedback, right? Expand, contract, expand, contract. And it would have a very specific topological structure, meaning it would look in a very specific way. It would have very specific dynamics for things to be able to expand and then contract and so on. So, when you think about it, and I was thinking about it for years, if you radiate, if you look at the universe, you find that everything in the universe radiates. What does it radiate in? In the vacuum. the vacuum of space. Well then, the vacuum cannot be thought of as empty, can it? Because no energy is lost, no energy is gained. So if all the suns, all the stars, all the galaxies, all the black holes, everything we see radiates into the vacuum, then the vacuum must be full. Full of energy. And it was clear to me that then the vacuum must be the contractive side of the event horizon, the contractive side of the structure of reality, the part we don't see. Why? Because it's contracting towards infinity. Puzzled about that, and I remembered my first class of physics. So again, you know, I'm all excited now. I'm about 16, and I'm going to my first class of physics. Well, actually, I'm like 14 or, 15, something like that. And I'm like, oh my God, today I'm going to go into my first class of physics. I'm going to learn everything there is to know about atoms and reality. So when I sat, the first thing I did is put my hand up, and, the teacher didn't know me better at the time, so he asked me what I wanted. And I said, what is an atom? I was surprised to hear the response. I thought, oh, he's just going to spell it out. What the heck is an atom? And he said, oh, that's way too complex for a first physics lesson. And in fact, we are not quite sure what an atom is. I was like, huh? You mean that in all of the years of physics that have been going on this planet, you guys still don't know what the heck is an atom? How can you tell what anything else is then? Right? And so I was like puzzled, but one thing he said is that one thing we know is that the atom is made out of 99.99999% space. And I went, oh, space. Mostly space. Everything you see, everything you touch, everything is mostly space. 99.99999%. That includes you. So I started to think, maybe it's the exact contrary. Maybe the atom is just a result of a division in space. Aha. Like the fractal structure we just saw. Divisions of space to infinity. Now it starts to look a little different, doesn't it? Is your brain starting to hurt? That's okay if it does. So space, reality could be just various resolution, right? Various divisions of space in a fractal structured vacuum. There is two infinities in physics. That sounds like a misnomer, but that's the way it is. One infinity is infinitely small quantities. You mix this quantity with this quantity and you approximate it and, infinitely small. At one point you say, okay, well, it doesn't matter, it's just bits, like infinitely small. It's okay, you can ignore infinitely small. And then there is another infinity. That one has a highly technical term that is found in physics books, and that term is nasty infinity. there's a thing in physics is that if you find nasty infinity, you gotta somehow get rid of it. And if you don't, then your theory is no good. It's discarded. And the way they came up with a way to get rid of it is that they use a renormalization process. Basically, they take the infinitely large number and they cut it. So how did they renormalize this? Well, they took a thing that's called a Planck's distance. And I'm not going to go into much details on how they derived this number. But it has to do with the Schrödinger's equations. And the Planck distance is 1.616 multiplied by 10 to the minus 33. This is a small little dot. And basically they say this little dot is the smallest thing the universe does. Right? We'll make the dot. See? Here's my Planck's length. And they say the universe goes to that small and then stops. It's like, I'm done. I'm out of here. This is way small enough. I ain't doing nothing smaller. Let's go with this. The universe is expanding. The vacuum is contracting to infinity. And all of reality emerged from the feedback between expansion and contraction.
I want to talk about Nassim Harameyn's recent paper on the Schwarzschild proton, which was not only accepted but chosen by a panel of 11 peer reviewers at the University of Liège in Belgium to win the prestigious Best Paper Award in the field of physics, quantum mechanics, relativity, field theory, and gravitation.
You know, if you have children, if they go to school, they're all going to get told that the solar system looks something like this. Planets go around like this in an elliptical course. Well, that is absolutely incorrect. The thinking of the solar system in this matter is equivalent to thinking that the Earth is flat. In fact, the sun is moving through space and the planets are flying around the sun, generating these huge vortices as it follows the equator of the sun. That is a completely different picture. All right? It goes from flat to spacious, to movement through space. And that makes a big difference. All of a sudden, you start to see that even planetary motions, solar motions around the galaxy, galactic motion, supercluster motion, and so on, all have this elliptical, vorticular dynamics of space. They all have this torque dynamic through space. Let's go back to the analogy of Einstein's field equation of the trampoline curving to generate gravity. So basically Einstein said gravity is the result of space-time curving like the surface of a trampoline. And basically what we say in this paper is that yes, and when space-time curves, it doesn't just curve, but it curls, just like water going down the drain, and that generates spin, angular momentum. And that's the source of the spin of all things. So when we add torque to space-time, the solution gives us a very different picture than a perfect sphere. It generates a torus structure, okay? Which is a sphere with two holes in the middle at the north and south pole. The result is a double torus structure, a double torus manifold, that has this dynamic, which is viewed here from above as a rotating yin-yang sign, if you'd like.
This significant paper marks a new paradigm in the world of quantum theory, as it describes the nuclei of an atom as a mini black hole, where protons are attracted to each other by gravitation rather than some mysterious, undefined strong force. This radical new view of the quantum world produces a unification of the forces and appropriately predicts measured values for the nucleons of atoms. It begins with the quantum vacuum density, which is a measured 5.16 times 10 to the 93rd grams per cubic centimeter. Then we calculate how much vacuum energy would exist inside of a proton, which has a radius of 1.32 femtometers, multiplied by 4/3 pi r cubed to get the volume. A density is mass per unit volume, so if you multiply a density by a volume, the V's cancel to give the amount of mass that would be contained within a proton volume, which is 4.98 times 10 to the 55th grams, which also happens to be the mass of the entire universe, existing inside each and every proton. Nassim also believes that this is evidence of an ultimate entanglement of all protons, which he mentions briefly in his paper. Just think of every single proton inside every single atom in your body connected through the vacuum to every other proton in the universe. We then calculate what proportion of the total vacuum energy density available in a proton volume is necessary for the nucleon to obey the Schwarzschild condition for a black hole, where the radius of our black hole is now 1.32 femtometers, the radius of a proton, and we solve for m. The mass needed to obey the Schwarzschild condition for a proton radius of 1.32 femtometers is 8.85 times 10 to the 14th grams. Harriman then uses this mass to calculate the gravitational force between two contiguous Schwarzschild protons using the semi-classical approach. We yield a gravitational force of 7.49 times 10 to the 47th dynes. If we then calculate the relativistic velocity of two Schwarzschild protons orbiting each other with their centers separated by 1 proton diameter, we get 2.99 times 10 to the 10th, which is also equal to the speed of light. This essentially means that the protons inside of a nucleus can be thought of as black holes orbiting each other at the speed of light. A fascinating concept. If we then calculate the period of rotation of this system, we get 5.55 times 10 to the negative 23 seconds, which also happens to be the characteristic interaction time of the strong nuclear force. So apparently the strong force is actually quantum gravity at work due to the black hole nature of the Schwarzschild proton. Now it turns out if we plot every object in the known universe onto a logarithmic scale of mass versus radius, we find an approximate linear progression. Oddly enough, the Schwarzschild proton sits almost exactly on this line, while the standard model proton sits far outside, suggesting that the standard model is incorrect after all. I also liked how Nassim showed how one can obtain similar results by using the proton volume to Planck volume ratio multiplied by the Planck mass to get the same result of 4.98 times 10 to the 55th grams, the entire mass of the universe inside every single atom. This is important because the Planck length relates directly to the Fibonacci number and phi golden ratio, which is a key mathematical element in all self-replicating systems. The question is, what is replicating itself, and why?